title is Embedded Minimal Annuli Touching Spheres.
Yeah. First of all, I would like to thank the organizer, my former advisor, and my topic is embedded minimal annuli touching spheres. The question is very intuitive. I was interested in this problem. Suppose that sigma is a compact embedded compact embedded, probably embedded minimal annulus meeting two spheres in constant contact angle along each boundary. In this picture, the solid lines are spheres, and the boundary curves or intersection curves are the dotted red lines, and the contact angle is constant along each boundary curve. And the question is sigma or catenoid? And
two spheres can be disjoint?
Yes. And in this picture, the spheres looks like have same radius, but they may have different radius. So let me start with the definition of catenoid. It is well known. It is obtained by rotating the catenary around the g-axis, and it is well known that catenoid is the only non-planar minimal surface of rotation in R3, up to homothety, of course. Then if I let S be a sphere centered at some point on the g-axis, then the contact angle between S and the catenoid is constant. So my question was very natural to ask, and there are some related results. If I replace two spheres by two planes, parallel planes, and consider a slab, then there's a result like this. If A is a compact minimal, possibly immersed minimal annulus in a slab, and if A, the minimal annulus meets the boundary of slabs in constant contact angles, then the minimal annulus is part of a catenoid. And the second result is this. If A is a compact embedded minimal surface in a slab and the contact angle is constant also, then A is part of a catenoid. This second result can be proved by using the Alexandrov reflection argument. And in a ball, in the case of ball, there is a result by Nietzsche. He showed that if D is a minimal or CMC disk in a ball meeting the boundary sphere of the ball in constant contact angle, then the disk is actually a spherical cap. So if D is minimal, then it is a flat disk, and if it has a non-zero constant mean curvature, then it is part of a sphere. And Ross and Swam obtained some results about stable things in a ball. And the next result is about complete minimal annulus. It is obtained by Cho, and he showed that if A is a complete minimal annulus with a closed boundary on a plane P, and if the contact angle between the annulus and the plane is constant, and if A has a finite total curvature, then the minimal annulus is part of a catenoid. So this was my kind of motivation, and there are three problems I wanted to introduce to you. The first one is related to Nietzsche's result. It says if A is a compact minimal annulus in a ball meeting the boundary sphere perpendicularly, then it is A part of a catenoid. Yeah. So I have a sphere here, and part of a catenoid meeting. It is a trivial example, but you may ask whether there is another minimal annulus or satisfying this condition. And in the case of a constant mean curvature surface, there are counterexamples. When he constructed immersed CMC annuli, which is not rotational, it is not part of a Delaunay surface, and the contact angle is 90 degrees. Yeah, it was proved about 15 years ago. And the second problem I want to introduce to you is this one. Let B be a compact minimal annulus meeting two spheres perpendicularly or in constant angles. And I may ask whether the minimal annulus is part of a plane or part of a catenoid. Yes. In this case, I have two concentric spheres, and the dotted lines are gray circles, and the green piece is part of a plane meeting two spheres perpendicularly. So the last problem is this, is about complete minimal surface. Let's see the complete minimal annulus with boundary on a sphere. Suppose that C has finite total curvature and meet the sphere in constant contact angle. In this case, I suppose that the contact angle is 0, but I may suppose non-zero constant contact angle. Anyway, I may ask whether C is part of a plane or part of a catenoid. About the problem 2 and problem 3, I obtained partial affirmative answers. So I'm going to introduce you the results, and I will prove this thing. Hopefully. Yeah. The first theorem says that if sigma is a compact embedded minimal annulus in R3 meeting two spheres of same radius, I may assume that the radius is 1 and that the contact angle is 0, then sigma is part of a catenoid. And the second result says that if I replace a sphere by a plane and the contact angle is bigger than or equal to pi over 2, the contact angle is measured from inside. So I'll explain about this angle alpha later. Then sigma is part of a catenoid. And I'm working with Junchol about the complete minimal annulus case, and we obtained the following results. Let sigma be a compact embedded minimal annulus meeting two concentric spheres perpendicularly, as the picture I showed you earlier, the green one, this one, like this one. Then we proved that it is actually part of a plane. And the second result is says that if sigma is a complete embedded minimal annulus with boundary on a sphere, and if sigma has finite total curvature with contact angle 0, that means the minimal annulus meets this sphere tangentially and is a graph over some plane. So then let me explain what this means. In this, I have two pieces of catenoid, and this upper piece is a graph over some plane, but the lower piece is not a graph. So we proved for this upper piece type, but we could not prove for this lower piece case. I actually extended the result to CMC surfaces. So there are Delaunay surfaces, and I showed that if sigma is a compact embedded minimal CMC annulus meeting two spheres of same radius tangentially, and the Gaussian curvature is never 0, then sigma is part of a Delaunay surface. And I proved for the case of sphere and planes. In this case, if the Gaussian curvature is negative, then the contact angle is positive. And if the Gaussian curvature is positive, then the contact angle is smaller than or equal to pi over 2. Sorry, I did not explain about this contact angle alpha. So here, if I take a plane passing through the neck of the catenoid, then the contact angle is pi over 2. If I go up, move the plane upward, then the contact angle is bigger than or equal to pi over 2. If I go down, then the contact angle is less than or equal less than pi over 2. So I'm considering only the cases of planes above the neck. I'm going to prove the result, but I hope it is not boring. Yeah. So first of all, there is a special curvature, special conformal coordinate on our surface sigma. So it is a conformal curvature coordinate. The existence can be proved in the following way. Let y be a conformal parametrization of sigma. Here I have sigma and y is a parametrization. And define x by y followed by exponential. So x is from the band to this sigma. X is 2 pi periodic, and I define z and lambda square with lambda positive. Yeah. Then the Hopf differential dg dg square is holomorphic for CMC surfaces, and the theorem of Joachim-Stahl says that gamma 1 and gamma 2, the boundary curves are curvature lines of sigma, because sphere is totally oblique, yeah. And the contact angle is constant. So this implies that H12 is 0 on u equals 0 and u equals log r. And H12 is a harmonic function and periodic, so it is identically 0 on the whole strip. And that means G is a curvature coordinate, and H11 minus H22 is a constant, is a real constant. And because sigma is minimal, it is equal to 2 times H11. And we fix the unit normal vector field on sigma in such a way that H11 is positive. In the picture, n is pointing outside. I mean, yeah. And in this case, with this curvature coordinate, the principal curvatures are H11 over lambda square and minus H11 over lambda square. Yeah. And I need a lemma. It is a very elementary lemma. And first I have the principal curvature kappa 2 is minus 1 on the boundary curves. Yeah. And then secondly, at interior points of sigma, lambda square is always smaller than H11. Therefore, the principal curvature is bigger than 1. Kappa 1 is always bigger than 1 at interior points, and the kappa 2 is always smaller than minus 1 at interior points. And finally, as spherical curves, gamma 1 and gamma 2 are convex. This proof is very elementary. I compute the curvature of gamma 1. It is like this. And because gamma 1 is a spherical curve, the inner product of kappa and gamma 1 is minus 1. And I take inner product with gamma 1, but because the sigma is tangent to the sphere along gamma 1, the normal vector n is equal to gamma 1 is equal to position vector. So I actually take inner product with n, and it is this, yeah, and this one is -1. So I have this result, the first result, and the second result can be obtained by using this equality equation. I can rewrite the equation like this, and lambda square was constant on boundary curves, so I have this, and the Gaussian curvature is negative because the surface is minimal. Therefore, lambda does not have interior maximum, and it means that lambda square should be always less than h11 at interior points. So I proved the second result, and the final third result can be proved as follows. First, we note that lambda u is non-positive on the boundary, on the left boundary, and is non-negative on the right boundary. And xu over xu is perpendicular to the curve gamma I. So the geodesic curvature of gamma I is the inner product, this inner product, and this is equal to minus lambda over lambda squared. And we showed that lambda u does not change sign, so gamma 1 and gamma 2 are convex spherical curves. And I need the -1 parallel surface to prove my theorem. The -1 parallel surface is defined by this equation. So if I take the center of S1 as the origin of R3, then x goes like this, and n was pointing outward, outside, then I go in this direction again. So the x tilde may look like this, yeah, in some sense. And I can actually compute something. First, sigma tilde, the parallel surface is possibly singular. I showed that lambda square is minus h22 on the boundary curves, and x tilde v has length 0. So sigma tilde is singular on the boundary curves, and this is okay because h11 is positive. And for minimal surface sigma, the Gaussian curvature and the mean curvature is equal for -1 parallel surface. Actually, I can compute the principal curvature of sigma tilde, and its sum is this, and it is equal to this one. And locally, I can represent sigma tilde as a graph of function f, and f satisfies this partial differential equation. I'm going to use this later. To prove my theorem, I considered the -1 parallel surface, and I actually showed that sigma tilde is embedded convex surface with 2 singular points. The convexity of sigma tilde can be proved as follows. Sigma, I told you that sigma admit a single component coordinate with this property, and I showed that kappa 2 is always smaller than or equal to -1, and the kappa 1 is bigger than or equal to 1. And the principal curvature of sigma tilde is either bigger than or equal to 1/2 or bigger than 1. Yeah. So if I replace 1 by 2, then I plug in this inequality into this, and I get this inequality. And finally, I considered the tangent cone of sigma tilde at singular points of the tangent cone is actually convex because the tangent cone is the cone over this curve, spherical curve with the apex O, the center of S1. And since gamma 1 is convex, I should erase this and this curve, spherical curve, is also convex, so the tangent cone is convex. Then I used the Alexandrov's theorem about closed convex singular surface in R3. Alexandrov showed that each closed convex singular surface in R3 is actually the boundary of some convex body. My sigma tilde is convex, so sigma tilde should be embedded. Yeah. Then I need to look at the partial differential equation, this partial differential equation is elliptic if and only if this matrix, 2 by 2 matrix, is positive definite. And here, this QF is the Hessian, and the A of dF is given by like this. And this expression is independent of choice of the coordinates, so I may assume that gradient is 0 at some point P. Then the determinant of this matrix is W to the 4, so it is always positive, and the trace is 2 times Laplacian of f minus 2 plus fx square plus fy square times W. And I need to show that this is positive, but I can assume that gradient of f is 0, and then Laplacian of f is the mean curvature times 2, and it is bigger than 1 at P because I have this condition. So I can show that the trace is bigger than 0 in a neighborhood of P. So this PDE is elliptic for me. Then I apply the Alexandrov reflection argument to sigma tilde. I fix the horizontal vector V, and I consider the planes perpendicular to V. I move far from sigma tilde and goes toward the sigma tilde, and I start to reflect the surface. And at some point, this red line represents a plane perpendicular to the vector V, and at some point the original surface and the reflected surface should be tangent at an interior point. And then I can apply the comparison principle for second order elliptic PDE, and then the original surface and reflected one should be same thing. So I obtain a reflection plane, symmetry plane. The symmetry plane should contain this dotted line, g-axis, of course. And since the horizontal vector was arbitrary, I can conclude that sigma tilde is rotational, And because sigma is a parallel surface of sigma tilde, sigma is also rotational, and rotational minimal surface is catenoid, so I can conclude that my surface was catenoid. It's catenoid. That's all what I wanted to say today. Thank you. Thank you for your attention.
Are there any